So what does he want from us? He said there is a tank, and that tank has a negligible thickness, so the thickness is really, really small, and it has ice inside, and that ice sitting at 0 degree, and air around this sphere, and it's a sphere, it's not a cylinder, it's a sphere, is coming at 25 degree, that's T infinity, all right? And it's coming at 6 meters per second, that it's the V. Determine the rate of heat transfer to the tank and the rate at which the ice melts. And you give us how much joule does it take to melt 1 kilogram of ice, the heat of fusion. So required is the Q dot and the M dot ice that will melt. So if I can get you the Q, how can you get me the M dot ice? Anyone? If I give you the Q and I tell you that the Q is 3,000 what? How can you get me how much ice will melt per second?
5933.
Right, you would say Q is all those joules going to the tank will end up being M dot time the fusion heat, right? That Q is going to be M dot multiplied by the 337 kilojoule per kilogram.
So
I actually, if I were you, I will say joule per kilogram and multiply by 10 to the power 3. So that's how you can get how much ice will melt. All the joules going to the tank will, what will the ice do with it? He cannot just go from 0 to 1 to 3 to 5 degree. He first have to turn into liquid before he start heating up. Okay? So as long as there are two phases, ice and water, he will have to melt first before he can take the water and the ice to 1 degree. However, you can cool him, so that ice at 0, if you cool him, he will go to 1, -1, and he will get cool to -2. He wouldn't mind. He would not say, no, I have to become water first before I start. No, he's ice, he can go down. But he cannot go up before he turn itself to water first. The other question, yes? Okay, so this is how we can get the ice later once we get the Q, and that equation is worth 1 point. Now, how we are going to get the Q? A tank, spherical tank, air is flowing into it. Excellent. So Brandon is saying you should think about this as one temperature over here, T infinity, one temperature over there, and there are resistance that prevent that Q from occurring across that temperature difference. One of them is the convection, right? The other one is conduction in the tank. The third one is whatever happening in the tank, right? He said the tank is very thin. We didn't have the material, we didn't have the thickness. So Ts inside is the same as Ts outside. And because it's ice and it's sitting inside this tank for a very long time, there is no flow inside, there is no resistance inside to that, so it's actually the 0 go all the way to the surface. Alright? And so the Q just become the T infinity minus the T ice, right, over, or Ts, over 1 over HE. H, external forced convection. How can I get this H? So this equation again is worth 1 point. So how can I get my H? Right, we need to get a Nusselt number. So we open the chapter for external heat transfer and we look for a sphere, and there is this one equation for a sphere. And that equation is Nusselt number it's 2 plus 0.4 Reynolds 0.5 plus 0.06 Reynolds 2 over 3 the whole thing at multiplied by Prandtl 0.4, and you got mu infinity over mu s and power 1/4. And in that equation, we need the Reynolds number, we need also the parental, we need the k, we need the properties. And so the properties, if you open that equation, sorry, if you look at this equation, you will see that he said that the properties is evaluated at the free stream. For a sphere, the properties of that equation was at the free stream except for, of course, mu s. That's the mu at the s, and that's what's given here for us. So this is already the property at the free stream velocity. So all we have to do is just plug the k and the mu. And for the Reynolds number, so this equation is worth 1 point, and we need the Reynolds number. Reynolds is, of course, Vd over nu, and that Reynolds is worth 1 point. And so that Reynolds is 8, 4, 10 to power 5. And once you get the Reynolds, then you can get the Nusselt number, and the Nusselt number it turned out to be 812, and from that you can get your H, and so the H become 9.4 watt per meter square degree C, and from that you can get your Q, and the Q is 3580 watt, and m dot ice is 0.0107 kilogram per second, and those two guys, the two numbers together is 0.5, so each one of them is 0.25. So the final answer is 0.5, and the equation is worth.
I have a question about the range of Reynolds numbers that equation can be used for.
Okay, just a second. We have first, I didn't say the area. So in the Q equal HA, we also need to get the area. So that area is by d square, or 4 by r square. 4 by r square is the same as by d square, right? Because each to r is 1d. So that's, this equation is worth 0.5. And Jesse is saying when you look at the Nusselt number equation for a sphere in our textbook, and you look at the range of the where it will work, what does the range say?
3.5 to 8 to 10 times 10 to the power of 4.
So this range is a little bit higher.
Right.
So what you suggest? That's actually
that's where I ran out of time to test those. I was trying to think of what equation.
But that's a very good question actually. When we have an equation, and the equation is basically only recommended for a certain range, and we are outside that range, we shouldn't use that equation if we have an option. If we have another option, of course we have to switch to the other equation. We shouldn't keep using it because probably that equation will get a lot of error. But if this was the only equation that they have for a sphere, well, then you just have to use it, and you will just make a note that, well, it's really outside its range, and probably the error will be really big. And it will not really immediately, when you go outside the range that much, you know, it will not immediately drop from you, but it just that the error get bigger and bigger until you cannot tolerate it anymore.
I did write a note, but I didn't get to finish actually writing down the equation itself, but I said this is the only equation for a sphere.
So that equation will count. If you have it, then you will have it. You will get the points for it. Question about this solution. So you can see 4.5 for the equation and 0.5 for the answer. Okay?